In this video we'll look at the geometrical interpretation of a second kind of complex number equation. In this case we're going to look at the equation modulus of z take 3 equals the modulus of z plus 2i. Now recall that if we look at the modulus of z take w, where z and w are both complex numbers, then the geometrical interpretation of this is that it represents the distance between the complex numbers z and w. And we're going to make use of that property when we interpret the complex number equation that we've got written above. If we rewrite the equation slightly, so it's written in terms of the modulus of one complex number take a second complex number, the left hand side remains the same, so modulus of z take 3. The right hand side, on the other hand, we rewrite as the modulus of z take negative 2i. The left hand side then represents the distance between or from the complex number z to the complex number 3, whilst the right hand side represents the distance from the complex number z to the complex number minus 2i. So before we look at this algebraically, we're going to use the GeoGebra tool to look at this geometrically. So we'll go ahead and explore the geometrical interpretation of this equation. So we're going to use GeoGebra now to construct the set of all points at equidistance between the point u equals 3 and v equals minus 2i. So we begin by marking those 2 points rather than those 2 points in GeoGebra. Then if we draw a line segment between those 2 points, u and v. Next we're going to construct the midpoint between those 2 points along that line. So that will be one point that definitely is equidistant between u and v. Now if we draw the perpendicular bisector that passes through the midpoint A, before we do that we'll just show that it definitely is the midpoint there. So now we draw the perpendicular bisector that passes through A, and that gives us an equation or a line with equation minus 3x take 2y equals minus 2.5. That line will describe, or should describe, any point that is equidistant from v and u. So to demonstrate that, we choose a couple of arbitrary points along the line. So choose a point B, and then we draw a line segment between B and v and B and u, and then we notice that the length of each line segment is approximately 3.67, so indicating that they're both equidistant, or B is equidistant from the two complex numbers. We can do that with a second arbitrary point, which we mark as C. Again, we measure the intervals, or we mark the line segments, and we see that the length of both line segments is approximately 2.21. So having constructed our line of points that lie equidistant between 3 and minus 2i, or in other words the locus of the equation z take 3 equals z plus 2i, what we're going to do next is actually apply an algebraic approach to prove that this is in fact the locus of the equation. And what we do here is actually rewrite our equation slightly, so dividing through by minus 1, we get 3x plus 2y equals 5 on 2, which is equivalent to the equation that we derived geometrically. So in our algebraic solution, what we do is begin by defining z equal x plus yi. So substituting that into the left and right hand side, we get x plus yi take 3. The modulus of that equals the modulus of x plus yi plus 2i. Grouping the real and imaginary parts together and applying the definition of modulus, we get the square root of x take 3 squared plus y squared equals the square root of x squared plus y plus 2 squared. Next we square both sides and expand out our brackets, squaring both sides first and then expanding the x take 3 all squared and y plus 2 all squared. And you notice now we can cancel x squared on both sides and cancel y squared on both sides. And then rearranging our equation, we get minus 6x, bring the 4y up to the other side, so minus 4y. equals minus 5. That's taking the 9 over to the other side. And then dividing by minus 2, we get 3x plus 2y equals 5 over 2. Again, corresponding to the equation that we derived geometrically. So thus confirming that our geometric solution was indeed the correct solution.